Hello everyone, my name is Teng Liang. I'm a PhD graduating from the University of Arizona. Today I'm going to introduce our work submitted to ICC workshop. So our work is about enabling NFD to work out of the box at edge. NFD refers to NDN forwarding daemon. It's a software forwarder for named data networking. And in Indian community, people have been doing research for more than 10 years. And in discussion of NDN deployment, one argument is NDN is likely to be deployed at the edge first, because at the edge networks, it's easier to control all the devices, and TCP/IP may face more challenges in this environment. In the past few years, we made two observations when we see NDN deployed at edge. The first one is to run NDN applications between neighboring nodes require non-trivial network configuration. Specifically, you have to install NFD, configure it to set up routes and faces. And these configurations are non-trivial for application developers, especially when they want to demonstrate their applications. They suffer from all this network configuration. The second observation is that the forwarding behaviors in edge networks are not specified. Applications may expect the forwarding daemon to behave more aggressively, but currently these requirements are not satisfied. So all these observations motivate our work to design self-configured adaptive forwarding plane for NDN at the edge. So how do we make a self-configured forwarding plane? Our basic idea is we use self-learning as the base to develop our design. So the starting point is we want to avoid many configuration, especially the route configuration. What can we do to do that? The first way is we can run routing protocols, but still there's an overhead of setting it up and maintaining it. An alternative is we can use broadcast self-learning. That's the work published 3 years ago. And so we choose this approach, and I'm going to introduce how does this work. So the basic forwarding self-learning design is straightforward. So it answers 3 questions. The first question is, how do we discover data when there are no routes? The self-learning will broadcast interest to all potential faces. And broadcasting is usable in NDN because NDN has built-in loop detection. So even you have loops in your topology, you're able to detect that. So broadcasting becomes a very convenient approach in NDN without worrying about loops and those things. So self-learning will broadcast interest to all potential faces when there are no routes. And some of the faces may bring back data, some of them may not. Even though broadcast becomes a very common approach, we still want to avoid broadcast overhead because you are taking over a lot of network resources. To avoid broadcast overhead, one way is when the data comes back, you can set up routes because you know exactly which face comes back the data. So you know that face potentially has the data for subsequent interest. So you can set up the routes towards those faces. Then the next question is, which name prefix should we use for the routes, and how should we trust it? The idea in self-learning is we use a prefix announcement attached to the data. The prefix announcement explicitly tells the router, say, the first 2 name components should be used for your route name. And also the prefix announcement has a signature, so you have trust schema to verify who generates the prefix announcement and should you trust it or not. So this is the basic designs for self-learning. And we try to implement self-learning in NFD and with some initial testing, we find several limits of the original self-learning. The first limitation is the performance of multicast is poor in Wi-Fi. Like at edge networks, the most common access technology is Wi-Fi. That's where we do demonstrations, we testing our applications. And this is a well-known issue. The multicast in Wi-Fi performs much worse than unicast because it does not have layer 2 ACK. And in other wireless networks, it suffers from the same problem. The original self-learning, although it can learn routes, but it learns the routes towards the multicast phase, which performs bad. So we want to improve self-learning. So when we learn the routes, we not only learn route towards multicast phases, but we can also create a unicast phase and also announce the route towards those unicast phases. The second limitation is self-learning only learns one path. Even if you have multiple paths or producers in your local network, you only learn one. So you are not fully utilize the forwarding behaviors of multiple parties or multiple producers. So that's another improvement of our work. And also there are other forwarding behaviors in self-learning. The first one is interest retransmission is not considered, like the original self-learning did not specify how should it handle interest retransmission. And the second behavior is about NAC handling. When self-learning receives the NAC, it just sends it back. If it's a no route for NAC, it will clear a route. But it will it does not have alternative behaviors, which is too conservative. In our design, when we receive a NAC, if there are alternative parties, we still want the forwarder to try those parties before sending the NAC back. So this is more aggressive behavior, and the idea is to help the application to retrieve the data. Okay, so next I'm going to give an example to demonstrate after the improvements how self-learning works. Assume we have 3 devices in a local network connected in Wi-Fi, and one is consumer, there are 2 producers. Initially, when they boost up, they have the multicast phase by default, and there's no routes in their FIB. The FIB is a forwarding table, and NFD will forward the interest based on it. And initially, there's no routes in it. So in self-learning, how does it work? So it will broadcast the interest to all the potential phases. And this interest will send only once to the multiple phases. The animation shows 2, which means the interest will be sent to the both producers through the multicast phase. And let's assume these 2 producers, they have the data, and they will send the data back because they the data satisfied the interest. And the self-learning, when you receive the data carries a prefix announcement. The self-learning will learn the routes and the phases. So at the consumer NFD, it will create 2 unicast phases towards both producers. And it also will announce the prefix towards them. Let's say it's /A. So all the interest under /A will be forwarded to these 2 unicast phases next. So as a result, the interest will be sent back to the producer in the first producer, let's say. So this will avoid interest broadcasting because you find the best next hop and it will send the interest to the producer. And when we are talking about NAC handling, if the producer, the best producer is down, your interest sends to that producer will generate a NAC back because there's no route at the upper producer. So the neck sends back through phase 1 will clear the route towards that phase. So the subsequent interest and also the neck will triggering the interest to try alternative path. So that interest, when it receives neck, it will check the fib to say there is an alternative path. So it will send the interest to phase 2, and also subsequent interest will all be sent to phase 2 to the second producer. And also the data come back. So by doing this, we can achieve this failure handover to try alternative path without the consumer retransmit any new interest. So this is all the designs we had to improve self-learning. And next I'm going to introduce the evaluation. We implement the described features in NFD and we test it on real devices. We tested on 3 laptops connected to a home Wi-Fi. The laptops, here are the configurations. They're just normal Apple laptops. And the home, here is the home router model. The applications we use, they have different behaviors. One is NDN ping. The other one is NDN cat chunks, put chunks, which will download the file with congestion control. And we'll also try the iVisa video streaming service, which is over NDN, to watch videos. The scenarios we did is, the first one is we just confirm the performance between unicast phase and multicast phase over Wi-Fi, and we use cat chunks and put chunks with only one phase setup and also the route setup, and to download the same size file, 500 megabytes file, and the statics are retrieved from the NDN cat chunks. And you can see for the unicast phase, the good put in the cat chunks is about 30 megabits per second, while the multicast performance is about 200 kilobits per second. So it's pretty bad in Wi-Fi phase. So this motivates our design to create phase, not only the routes. The second scenario is about performance of interest retransmission handling, which we added to the original self-learning. And also because we learn multiple producers, interest retransmission can work to, it can try alternative path. If you only have one path, when you receive retransmitted interest, you cannot really do anything. So the scenario we set up is originally we have only one producer, one consumer, that we run the NDN cat chunks and input chunks to download the file. And this is the upper scenario is what the self-learning, original self-learning does. It only learns one router and also one producer and also downloads from it. In the second setup, we have 2 producers in the same Wi-Fi. And the improved self-learning can learn both producers. So it actually have 2 paths, and it can utilize it by interest retransmission handling. And as you can see, here is the result. If we only have one producer, it's about 30 megabits per second for the good put. And when you have 2 producers, your self-learning learns both producers. And when the bottleneck happens at the producer, the consumer will keep increasing the window size until a threshold. And because the first producer can only satisfy a certain amount of interest, the retransmitted interest will send to the second producer, so the producer can satisfy some of it. So by doing this interest retransmission handling, self-learning actually can utilize 2 producers, and this simple mechanism can improve the performance about 20%, 25%. The third scenario is about failure handover. So we described in the same environment, we have 3 laptops, 2 are running producers, and this time we use iVisa streaming service. When using self-learning, the consumer will use the upper producer to watch the video. And if that producer is done, we kill that producer in the middle, so it stops serving the data. So the consumer will send the data to the lower producer and will continue fetch data. And the users will notice this producer, will not notice this failure handover, and it just automatically downloads the data. And the last scenario we test is more than one next hop. We have multiple next hops to simulate, like in a multiple hop local network. You have a gateway which has the route, but all the other nodes does not have the route. Self-learning can still work in this scenario. All right, so this is all about this work. There is no real-time Q&A. If you have any questions, please send your questions to this email address. And thank you for watching my presentation.